Well, I'm going to talk about radiative transfer theory and in particular numerical modeling. What I'm going to talk about won't be specific. Well, it will start out kind of generic, and then later on it'll be more specific to the software Hydrolite, because that's the one I'm most familiar with, and that's the software we're going to be using in the practical afterwards in this afternoon. But, you know, a lot of the problems involved in numerical modeling of radiative transfer are kind of generic, and other models have to solve the same problems. They might do it in slightly different ways. So I will explain a bit about that kind of thing. Let's start with an introduction to myself, to you. I am John Hedley. I think I've kind of met most of you already now, said hi at least. My background is, like many people in this field, you know, I came to this field from a not very obvious route. It's very common, actually. You find people who come to this field from lots of different backgrounds. My undergraduate degree was in zoology, actually, nothing to do with physics or maths or remote sensing or anything like that. But then I did do a PhD in remote sensing of coral reefs. So that's how I started to get into this kind of field. For nearly 10 years, I worked in a coral reef ecology research group at the University of Exeter. My supervisor was a guy that had done remote sensing of coral reefs in the late 90s, sort of kind of early work on that stuff. But he was getting out of the remote sensing kind of thing. He was more into ecological modeling. And I was kind of the last person in the group doing any remote sensing. I was in that group for about 10 years. I just got more and more into the radiative transfer modeling side of things because my inclination is computer programming. That's what I like. I do a lot of software development, always have done, even before I did my degree. I was into that stuff. So I got more and more into the radiative transfer modeling side of things and developing algorithms for shallow water mapping, this type of stuff. Then that group moved to the University of Queensland, or a large number of them did. The group didn't exist anymore at Exeter. So I didn't go, I stayed in the UK. I worked briefly in a commercial sector company for about a year, and then I started working in my own company as a consultant, which is what I've done now for maybe the last 12 years. So I work on things like numerical modeling of radiative transfer is still my key interest, but that sort of underpins more applied work generally. I do a lot of stuff to do with shallow water remote sensing. Tends to be I don't do so much like kind of production work. I don't make maps so much as I help other people to do it. So I have a software which I develop for satellite-derived bathymetry, and I provide that software as a product that I sell. And I do training in that kind of using that. And I've worked with hydrographic agencies, government agencies, academics, and commercial sector doing that kind of stuff. One of my main activities, or an important activity at least now, is since 2017, I'm the person that maintains and develops Hydrolite. So since Kurt retired, he passed that on to me. I sell it now I've continued to sell it as a commercial product. It's always been a commercial product. And I support the existing users and I support the new users. I maintain it. You know, if there's a new version of Windows and it stops working or something, I have to fix it, make it work. And I find occasionally little bugs. There's not many bugs in it, but I sort of fix things. And I'm also in the process of developing a new version of Hydrolite, which this is being recorded now, so it's going to be sort of on record. But I hope by the time this course is run again on the next Ocean Optics Conference, there should be a new version of Hydrolite out, which will have some new features and hopefully be of interest. But I'm not going to say too much about that because it's like I'm committing myself on recording about what's going to happen, and I'm not quite sure at this stage, but I am working pretty hard on that at the moment and I'm making quite good progress. I'm also interested in benthic photobiology. That's another aspect, but I haven't done much work on that recently. So, so I don't really do field work. I just sit behind a computer. But earlier in my career, I did do field work. I was involved in one project I was involved in was a World Bank GEF funded coral reef targeted research program for capacity building, I think it was called. And we went around there was different working groups. There was a remote sensing working group, a photobiology working group, and some other working groups. I was in the remote sensing working group, and we went around various sort of centers of excellence and different places, taking IOP measurements coincident with airborne imagery, this kind of thing. And this was in Bolinao in the Philippines, and this is our pointer here. You can just see the ACS profiling cage there on our deployment vessel. in the Philippines there. So that was kind of a fun time, but that was pretty much the last time I've ever done any actual practical field work using ACSs and stuff like that. So I've got a bit of an understanding of that. But ever since then, I've just been stuck behind a computer. So I like to get out and about as much as possible in my non-professional life. And I'm quite lucky that I live, I think I should highlight this, but this is where I live here in the southwest of the UK, where this dot is. And I'm lucky because I live between two national parks, which is Exmoor and Dartmoor. So the countryside is really good where I live. And actually, I can literally just walk out of my house and walk into really kind of nice areas with good scenery and sort of oldie, worldy English buildings, just like you see on TV programs, depending on which programs you watch, you know, these sort of thatched cottages and stuff. That's the environment in which I live. So that's really nice. So I like to get out and walk and cycle. And also surfing's really good on the North Coast. I mean, the surfing's good, but I'm a terrible surfer, but I do some of these kind of things. So that's one of the things I like to do in my spare time, to get out from behind the computer. So now back to the topic of the lecture. Okay, so this is a simplified version of the diagram that David showed, really, which is, you know, what you've been learning about so far, which is, you know, the constituents of the water column dictate the IOPs, and you've seen that from Darius's lectures and so on, how the different particle sizes and so on can lead to different absorption, scattering properties of the medium, bulk medium, when you add them all together. And what we're interested in remote sensing is things like reflectances, other radiometric quantities and properties that you derive from those, as David was talking about. And what links these together is radiative transfer theory and what we have referred to as the boundary conditions, which is in essence the sky radiance that's input to it. So you've got the sky radiance, you've got the optical properties of the materials. Somehow something happens with all of that, and then you have radiometric things that you can measure radiometrically, the AOPs, which you would derive from that as well. So radiative transfer theory is the thing that links these two. But what I'm talking about more is the more practical side of that, which is a radiative transfer model. So a radiative transfer model is essentially the embodiment of the radiative transfer theory. We have theoretical concepts about what happens to the light, and we need to manifest that in an actual software code. And what I'm going to try and do in this lecture is talk about, I want to give an intuitive sense of what's necessary to make a software code that can do this. I haven't got very many equations, you'll probably be pleased to hear, although I have got one. I have got the important equation, which you've already seen several times. You're going to see it again, the radiative transfer equation. But apart from that, I really just want to give a sense of the problems involved and how they're solved by various models and the hydrolite in particular. So how can we do this? How can we take the input radiance, the IOPs, and turn it into the actual radiances and reflectances and so on that we want to know? So I refer to this as a forward model, or this is what we would call it, a forward modeling exercise. What we're actually interested in when we do remote sensing is the opposite, which is the inverse problem. So I'm talking almost exclusively in this talk about forward modeling. Okay, so why is it useful to have a forward model? Well, we can understand how the IOPs relate to the AOPs, as we've just been talking about, characterize the relationships between constituents and the reflectance or other measurements we might make in the water column. It's really useful for feasibility studies. So you might want to think, well, can I detect a change in a certain mineral in suspension if I have a certain concentration of it? What's the effect going to be on the reflectance? And does that effect fall within the bounds of the signal to noise ratio of the satellite or whatever that I'm going to be using? So you can do sensitivity analyses if you have a forward model. You can look at the consequences of the variability of things on remote sensing reflectance. So Darius talked a lot about, like, okay, you can have a certain species of phytoplankton, but under different conditions, it might have different optical properties. The cells might be bigger, the pigment packaging might be different. So that's going to give a variability in the IOPs. But actually, what you really want to know is what's the variability in the reflectance. If it's a remote sensing objective, you know, is that variability actually reflected in the reflectance? You might be lucky in that there might be a lot of variability, but it might not actually make that much difference to the reflectance. So you can use models to kind of assess this kind of thing. like what's the consequences of these variabilities. You can use forward models to develop inversion algorithms. So the simplest way to do that, or a simple way to do it, is to run the model over and over again to get different reflectances, different input parameters, and you build a big table of the reflectances from the model based on the different input parameters, and then you can do spectral matching, where you take your reflectance from the satellite and you find the reflectance that matches the closest, and you say, okay, these are the optical properties in the water. So that's a simple spectral matching through lookup table inversion algorithm. Or you can do things, if you're interested in semi-analytical algorithms like Zhongping showed, you can have components of an algorithm that you want to use a radiative transfer model to characterize. So a good example is maybe in your algorithm that you're developing, you need to translate between subsurface remote sensing reflectance and above surface remote sensing reflectance. So then you would have, you could run Hydrolite over and over again, for example, or another model to compare with different input parameters and compare the remote sensing reflectance below surface and above surface and make a regression. And then you can use that regression in your semi-analytical model to do that conversion. So it's useful for components of semi-analytical algorithms. And also, nowadays machine learning is really kind of popular. So you can train machine learning. You could use a model, again, running it with lots of different input parameters, different optical properties of the water, and then use that as a training data set for a neural network or some other machine learning technique. And finally, which I think is really important, and it's kind of the focus of this afternoon really, is you can use a model as a learning tool to help build an intuitive understanding of hydrological optics. You can run the model, you can look at the outputs, change the inputs, look at the outputs, and get an understanding, an intuitive understanding of what things affect different things. And that's very helpful if you're going to work in this field, obviously. So it's very useful as a learning tool. So David mentioned this, and I shall just reiterate it, that what we're interested in is the radiance. Spectral radiance is the fundamental radiometric quantity of interest. If you know the radiance distribution everywhere, then you know everything for our purposes. You can derive everything else from that. Now, an important part to realize here is that when we talk about radiance, we're talking about a measurement of the light intensity in a specific direction. That's what it is. It's a directional measure of the light intensity. But in practice, we'll use an instrument like this, and it's actually the same diagram from David's talk, that has a finite solid angle. So we say we want to know the radiance in this direction, but actually we can't know exactly the radiance. We can't measure exactly the radiance in that direction because it would require us to reduce this aperture to 0, and then we would measure no light. So in practice, we tend to measure at a small solid angle around the direction, and we say that this is the radiance in the direction we want, but as an approximation, essentially, from that small solid angle. We have a similar problem when we come to do modeling on the computer, because we cannot represent radiance as a continuous, effectively infinitely angular, with an infinite angular resolution. Radiance is actually in a specific direction, but we can't talk about radiance in a specific direction because we'd have to have an infinite number of numbers to propagate through our model. So actually, this is one of the main ways that different radiative transfer models vary, is in the way they sort of handle this problem of how to handle the angular directional radiance, because you can't really do the exact thing that you want. You have to have some kind of angular resolution or a concept of angular resolution in there. And again, David mentioned this. There's two ways to look at this, or two possibilities. You can have scalar radiative transfer, which completely neglects polarization. So we don't have any polarization in the equations, and we just treat everything as an unpolarized interaction. That's not really what happens in the real world. In real life, light is polarized or can be polarized, and it can make a small difference, which I'll come back to. And actually, David already kind of gave away the answer there, because it does just make a small difference sometimes. Hydrolite is only a scalar radiative transfer model at the moment. Some other models can do vectorial radiative transfer, but pretty much everything in this talk is going to be about scalar radiative transfer. I won't mention polarization again. So we're just talking about a situation where the interactions don't involve polarization. I will return to this later. Okay, so let's gain an intuitive understanding of the problem to be solved. So in the first instance, let's imagine there is no scattering, only absorption. And the light comes into the ocean like this. What color will the ocean be? It's the test question. Black, exactly. If there's no scattering, the light will come. In fact, you don't even need the condition that there needs to be any absorption, because if there's no scattering, there's nothing to turn the light around and make it come back out. But in this case, we've only got absorption. So the light comes in a certain direction, shall we say. So imagine light traveling in a certain direction, and it just gets less and less as it's absorbed, as it goes forward along its path. And the rate of absorption here is governed by the absorption coefficient, A. Now, if we introduce scattering in this beam, so the beam comes in, now it's getting absorbed, but also occasionally it's getting scattered. And the rate of scattering, or how often scattering occurs, is governed by the scattering coefficient, B. So the losses to the beam are the losses due to absorption and scattering. A plus B equals C. This is what you've seen already. C, the attenuation coefficient. So we have this beam, and it's just getting less and less and less, and light scattering out and scattering in. And this is what we might call a single scattering approximation. We only allow a single scattering event on any particular path. And actually, early in this field, single scattering models were quite common. You know, it's a relatively simple thing to develop a single scattering model. It misses out a lot of the complexity, but it does get you what we would call like the first order solution. And they're still useful, because sometimes if you want to just get a handle on something, you can quickly code up or devise a single scattering model and just get a feel for what's going to happen. Now it gets more complicated though. Oh yeah, single scattering. Oh, the scattering angle when it occurs is determined by the phase function, which you've also heard about. So this diagram is a little bit misleading, because it shows scattering kind of happening in all sorts of directions, which it does, but predominantly the scattering when it occurs is in close to forward directions, as you've seen, because the phase function is very forward peaked. So actually what you would really see is the light coming in, and a lot of it scattering in forward directions, some of it coming off at these angles, yeah, but really scattering is predominantly pushing the light more forward. So that's determined by the phase function. So here's your three key IOPs: the absorption, the scattering coefficient B, absorption coefficient A, and the phase function, which determines the direction of scattering when it occurs. Now it gets more complicated, because what you have to consider is that not only do you have losses to the beam, but you have scattering into the beam as well. So light from other directions gets scattered into the beam, and that increases the radiance or the light energy in this beam. So now it gets complicated, because you have to think about the light in all other directions as well. So it's not just a question of the light coming in along one way. You have to start thinking all about the light everywhere and how it scatters into that beam. And then you've got multiple scattering. So of course it can scatter again, and you can have scattering under the water surface, and of course transmission through. And you've seen from the practicals how light incident on the underside of the water surface, if it's at a sufficiently shallow angle, will totally reflect in. So you get total internal reflection. So the light can bounce in back into the water, and actually the water tends to trap the light a little bit. So it will tend to, you can get these kind of multiple interactions under the air-water interface. These essentially are scattering events as well, but it's a different type of scattering. It's coherent because you've got the air-water interfaces like a surface, whereas here I'm talking more about scattering by particles, but it's all scattering at the end of the day. And also you can have elastic and inelastic scattering. So the way I've kind of presented it, or the first way you can imagine it, is the wavelength stays the same through all these events. But with inelastic scattering, you can also have a change in wavelength at scattering events. And the kind of processes you have is chlorophyll fluorescence, Cedon fluorescence, and Raman scattering. In general, we always assume that the scattering, inelastic scattering, is from a shorter wavelength to a longer wavelength, because there's an energy loss in that. And that is almost always true, apart from Raman scattering does have a small component that goes the other way from a longer wavelength to a shorter wavelength. But actually, that is almost pretty much ubiquitously ignored in hydrological optics for our purposes anyway. Hydrolite doesn't include that backward term, and I don't think a lot of models don't include inelastic scattering at all. So we don't worry too much about that small component that goes the other way. Yeah, so okay. And then the other thing that you might have is bioluminescence. And if you have bioluminescence, then essentially you've got light just created. It just appears somewhere in the system. So you might want to account for that if you're interested in modeling bioluminescence and the effect on the light field in the ocean. So if that wasn't complicated enough, what we have to bear in mind is that the optical properties of the medium, the water, might change spatially. So you might have a layer of phytoplankton here. So you can imagine all these complicated paths that occur. Well, some of them might go through this layer of phytoplankton, then scatter and come back out and contribute to the reflectance. Some of them won't even get that far. They'll come up here. Others might even do things like scatter and then travel laterally through the layer before they scatter back out again. So the effect of a layer of phytoplankton in the water might be very complicated. Well, it is complicated to understand all of these things. So it's a very complicated problem to do a good job of modeling this. So if we had a perfect model and we could get what we wanted, what we would really want is the radiance distribution at every point in space for every direction. So this is just a reminder of the coordinate system that I'm referring to. Now, this is radiative transfer modeling. So when I'm doing this stuff, I'm always thinking about the direction of propagation. David mentioned this. If you have sensors and you're working with sensors, people will often talk about the direction the sensor's looking in. And that can cause you some trouble when you have to try and reconcile things. But I always think in terms of the direction of propagation. So here you have theta, which is the angle to the vertical. So this is this angle. And then phi is the relative azimuth, like that. So at any point in space, I can be looking, and it's like as if I have a sensor, or if I just look with my eye and I see around what is the radiance distribution. And the radiance is it's a large radiance when I look at these lights. So at certain points in the sphere of all directions, I see bright lights like this, the high radiance. In other places, it's lower. But basically, I can look everywhere, and I always see a radiance. If I move slightly to the side, it's going to be different. So spatially, every point in space, you have the sphere of all directions. And that is the complete radiance distribution within a space or a volume that we're interested in. If you can characterize that, you'd end up with something like this, which would be a 6-parameter model or function, x, y, and z being the position in space, theta and phi being the relative position on the sphere of all directions, and then lambda being the wavelength. If you know this, you know everything. This is the aim. This is ideally what we would have from coming out of our radiative transfer model, because then we can derive everything else. The irradiances, any radiometric properties we're interested, any radiometric quantities we're interested in, and then from then we can determine the radiometric properties. So I'm trying to be careful to say this exactly right, because David made this distinction between radiometric quantities and properties. So we know this, we know everything. Any questions so far, by the way? If you have a question, just stick your hand up or shout out, get my attention. Yeah, okay. Oh, yeah. Yeah. Yeah, well, this would be a question for Darius, but my understanding is it's something like you can add 2 energy states like kind of quickly, I guess, or something like that, so you can ramp up. A physicist friend of mine once said, and this is probably not at all helpful, but he described it as Raman scattering being like when you hear a train coming towards you, and then when it goes behind, you hear the different sound, and then when it goes behind you, hear the sound change. He said, "Oh, it's kind of like that." But it didn't really help me. It probably doesn't help you. But it is some sort of energetic. I mean, this is slightly outside of my field. You know, it's of interest, as it were, because as a radiative transfer modeler, basically, I just take the functions that people will give me. But it will be something to do with that. It's to do with energetic states and the fact that, I mean, you can get it also in theory with other types of fluorescence, because if you have an excitation where you're already in an elevated state, you know, you can jump up to a higher state than the original excitation was, and then you drop down and you get a shorter wavelength. So in theory, it's possible, but it doesn't happen very often. And it's a small component for the Raman as well. Okay, anything else? I shall continue. Okay, actually, let me just have a bit of a drink of water. So it's complicated. Yeah, so far I'm talking like this is ambitious. I'm saying that I want this 6-parameter function to be deduced by my model. But the first thing we do, especially when we're working in ocean optics, is we make it a bit simpler by removing the dependence, the horizontal dependence, and having what we would call a plane parallel model. So in that, what we assume is that the radiance distribution at a certain point, if we move sideways, it's going to be just exactly the same. So it's plane parallel. Everything is the same in a horizontal plane. And that works well for open oceans because they kind of are, as long as you talk about time averaged radiance, because obviously on the surface of the sea, you have a wave like this. And so at any particular moment, you see this wave above you, it's not going to be the same here as it is over there. But if we time average, and this is what we're working with here, is a time averaged concept, you know, when you move across, it's going to be the same pretty much in open ocean conditions at the kind of scales we're interested in. So we make this approximation, and then our 3-dimensional problem becomes 1-dimensional, and our radiance only has Z. We get rid of the X and Y. We don't care about the horizontal position. So now it's got a little bit simpler. We're just talking about a directional distribution of radiance that changes as you go down through the water column. So how can we approach this in practice on a computer? How can we calculate this radiance distribution based on the input boundary conditions of the light field of the sky light field incident on the surface of the water, and the IOPs in the water, now only as a function of Z, because we've made it a plane parallel model. Well, the simplest way to do this is a Monte Carlo model, which I'm sure you guys have heard about. And in this, what we do essentially is very similar to the way I just described the problem, is we trace rays through the water. So in our code, we have a big loop, and in the loop, we first generate a ray, and a ray usually is best considered as a package of energy. You can think of it as a photon, but it becomes slightly problematic because you often have to split the ray. You can't split a photon. So you can imagine it as like a bundle of photons or a package of energy, and don't worry too much about the sort of photon concept. And you give that ray a certain direction, and then you propagate it through the water column, and you pick random numbers to decide when things happen to that ray. So the scattering events are governed by the B scattering coefficient. So you'll pick a random number, if in effect, without going into the math, you pick a random number and you compare it to B, and you decide how far the ray is going to go before it scatters. So then the ray goes a certain distance, and then it will scatter. Now, at the point of scattering, it's passed through a certain amount of absorption. So you reduce the ray by the absorption on the path length, and then you pick a new direction to go using the phase function. So you effectively pick another random number, compare it to the phase function, you can decide what direction you then scatter in. And you just do that over and over again to the ray until it either gets completely absorbed, disappears, becomes effectively zero energy, or it comes out of the water surface, and then you tally it up and say, okay, I've got a bit of energy coming out here at a certain direction. And you do it over and over again with many, many rays until you can build up a picture of the radiance distribution. So it works not only for the reflectances, not only for the water leaving energy, radiance, if you like, but also, you know, you can put in your code a thing to detect when rays go through, say, a certain Z position, and you can tally up the light there. And you can tally it up either as irradiances, or you can just look at the angle that it's going at and get an approximate radiance at that point. But basically, you build up a picture of the light field in the water column by just tracing loads and loads of rays. The problem with this kind of, I mean, this is a good technique. This is useful. a very useful technique, and it has not gone away, and it never will go away because of various reasons. One is there's a very close association between the implementation and the physical concepts. As you can see, it's pretty much exactly how I described the problem is directly manifest in the code. So you have the absorption, the scattering, and the phase function, and you apply those in ways that are basically exactly how you understand that they work to these rays. But the downside of these methods is they're very inefficient. You have to try and propagate many, many rays to get a good picture of the radiance distribution. And it kind of depends what you're interested in. If you're interested in places where there's not much light, like where the light has attenuated a lot, then you really have to do a lot of rays to get a good statistical picture, because you get statistical noise with these. So, you know, you run maybe 1 million rays, and then if you do it again with another 1 million rays, you'll find that there's a difference between them because it's statistical, you know, it's a statistical noise issue. So it can be difficult to get convergence to a really good solution, you know, for certain problems. And also things like, you know, if you have a sensor looking in a certain direction, how many rays do you have to trace before you get a ray coming into that sensor? Some problems are actually intractable using this. What you can do is do a reverse Monte Carlo where you trace rays backwards through the system from the sensor to the sun. But then, you know, you also have the sun is a relatively small target in the sky. So, you know, it's still quite inefficient for some purposes. But they are really good for validating other models and this kind of thing, because you can be more sure that you got it right when you coded it up than you can some of these other more complicated models. So they're a good, very good reference point. Right, radiative transfer equation then. So this is, you've seen this at least twice already, and David gave a little bit of a breakdown of it, but I'm going to talk more. I'm going to explain, you know, I'm going to break this down so you can sort of understand what's happening with this. It embodies the same concepts I've just been talking about, but it puts it into a mathematical formalism. It looks really horrible when you see it, but I'll show to you that it's not so bad, hopefully. So this is the one-dimensional time-independent scalar radiative transfer equation with no inelastic scattering, because you can have different versions of this, but this is what I've just been talking about. It's got no inelastic scattering in it in this. Oh, we'll talk about that more in a minute. But basically, this is without polarization, and it's for a radiance distribution that varies only with depth. Yeah, so that's why it's one-dimensional. So what you see here, L, this is what I've been talking about. This is the thing we want to know. This is the sphere, the radiance over the sphere of all directions at a certain point in the water column at a certain depth, Z. And what this first bit means, d dz, it's a differential equation. I don't know if everybody's comfortable with this kind of stuff, but basically it just means what is the change in this as you take a small step in Z. So as you come down a little bit, what happens to this radiance distribution? Now there's a cosine theta there. You think, oh, what's that? But that's just because it's for the direction. So if you're talking about theta, when you come down, theta 0 means you're talking about the light straight down. When you take a step down in Z like this, then the distance you travel is just exactly that, because the beam is coming like this way. When a beam's coming from an angle like this, then you take a step down in Z, it's a longer distance, yeah? So that's what the cosine theta is there for. It's just to give you that correct path length as you take a small step down in Z. So the first thing that happens is, just like I talked about, you have losses to the beam. And this is the first term here. You see it's negative, and the losses to the beam are the losses due to absorption and scattering, A and B. So this is how the coefficients come in here. And there, it's a small fraction of the current radiance. So what this says is you take a small step down, you lose a proportion of the current radiance, yeah, because a certain fraction of it is absorbed according to the attenuation, which is A plus B. So this is the losses to the beam. And then you have the in-scattering to the beam, which is the next term, and that has a plus on it there because it adds to the beam. And you see here, this is scattering. So it's governed by the scattering coefficient at that point. And then you have this, what looks like a horrible double integral, but all that's saying is go over the radiance at all directions. It's an integral over theta and over phi. So it just goes over the whole sphere and says how much light is coming from a certain direction, scattering into this particular direction that we're talking about, yeah. And that's why it has here the phase function. So basically you go over the sphere, you go, okay, you've got some light coming in here. This is the direction we're talking about. What's that angle? What's the phase function? That's how much light we have scattering in from this direction, yeah. So this whole term is basically the in scattering to the beam. And then finally, this is just a source term. So if you have bioluminescence, you just add that on at the end. And it just adds to the radiance at that particular depth. So this kind of describes how the radiance distribution changes as you take a small step, and then you can just do it over and over again, essentially. If you take a small step over and over again, you've got a radiance distribution. It just changes as you go down through the water column based on this equation. So that's all it is. It's not too bad, although it looks pretty horrible. Now, this is for inelastic scattering. No, elastic scattering. If you want inelastic scattering, there's two ways that we can do it. And one is we can actually modify this integral here to be an integral over wavelength as well. So then we integrate over, not over just the phase function, but the phase function effectively that brings in light from other wavelengths. So you would have a term here, it wouldn't be scattering anymore, it would be something that was a function of two wavelengths that would bring in the fluorescence from other wavelengths into that. And in fact, if you did it that way, you would have an equation that expressed fluorescence regardless of whether it went from longer to shorter wavelengths or shorter to longer wavelengths. And if you could solve the whole system, actually you could do all of that stuff. But it's actually too complicated to do it that way. And most models don't do it that way. What they usually do is put the inelastic scattering, any fluorescence, into the source term. Because what you'll do is you model the wavelengths one at a time, starting with the shorter wavelengths. So you do the shorter wavelengths, and then you've got the light distribution in the water column, which you can use to calculate the fluorescence at the longer wavelengths. And then when you come to calculate those longer wavelengths, you just put that fluorescence into the source term here. So we don't normally do a full integral over all the wavelengths to do the fluorescence. We just do the wavelengths one at a time and then put it into the source term. And you'll see this when you use hydrolite. This is the way it happens in hydrolite. And the key thing to remember is if you want to model fluorescence, you have to make sure you model the excitation wavelengths as well as the emission wavelengths. So because you need the light field at those excitation wavelengths to give you the correct fluorescence at the emission wavelengths. So if you're using the model and you say, oh, okay, I'm interested in fluorescence at, 650 nanometers or something, I'll just model from 600 to 700 nanometers. That's not going to work because it hasn't got the light field at the excitation wavelengths for the fluorescence. Yeah. So that's something you have to be aware of. Okay, any questions on that? No, good. Either it's clear or it's totally not clear. It's one or the other. But anyway, so when you get these slides, you can see I labeled these actually. I forgot to mention. There's the attenuation, there's the in scattering, and there's additional sources. Okay, so I'm going to talk now. I'm going to move on a little bit to talk more specifically about hydrolite, how hydrolite solves this. That hydrolite is a piece of software which solves the radiative transfer equation. There are other models that also solve the radiative transfer equation. But I'm going to, hydrolite's the one I know, so I'm going to explain some of the things about how hydrolite does it, which are actually similar to some of the other models that you can find around. So the history of hydrolite, I mean, this was developed by Kurt Mobley working with a guy called Rudi Pressendorfer, who was a really major forefather of our whole field of hydrological optics. He was one of the founders of this field. He worked with Kurt. Kurt, I think, was I think it was after Kurt did his PhD, was working with Rudi, and Rudi said, Rudi had been working out all these equations on paper, and computers were just coming in. So Rudi said to Kurt, hey, come and work with me. Can you maybe turn these equations into a computer code? And that's how Kurt got started in this stuff. And I believe he's told me that when he first started, it was still punched cards. The computers were programmed with punched cards back in those days. So back to 1978 was when it started. Kurt developed it. Unfortunately, Rudi died relatively young, so didn't really see the fruition of the work. But Kurt finished off the software, put in all the stuff that I'm going to talk about, and it's been a commercial product since 1998, and then currently has maybe over 200 users, probably more, might even be as many as 300 now in 30 countries, and it's used in many, many publications. I just did a Google Scholar search for hydrolite like yesterday, and it returned over 2,600 results. So I don't really know how to interpret that other than it's mentioned in a lot of things. Yes, so it's popular. It's been used a lot over the years. Kurt's pretty much retired now, like most of these guys. He's not 100% retired, but he's mostly retired. And in 2017, he passed on ownership of hydrolite to me. So now I maintain it and develop it. And it's a product of my company, my consultancy company, essentially, which is Numerical Optics Limited. It's a commercial piece of software. You know, there are other models out there that aren't commercial. You know, you can download free models and so on. You know, it's an interesting thing. How does a commercial software survive when there's free softwares? I don't know. All I know is that the commercial basis of hydrolite, it works for hydrolite. It works for what it is. I mean, the advantages are you have somebody like me who has a sort of slightly vested interest in it and will come and give talks and support it. You know, if you have a question, you can always email me. I'll help you out. If it doesn't work, I'll fix it for you. This kind of thing, you know. So that's the advantage of having a commercial basis for it. And it kind of works because it's popular. It always has been a commercial product, and that's no chance to change that because it's something that works for the community. And the latest version is version 6. I just mentioned that because there are still people out there with version 5, but version 6 is a free upgrade. So anybody who's got version 5, they can let me know and they get a free upgrade. And it's also available for Apple, Macs, and Linux now, which it wasn't previously. There's a document that Kurt's written called a Hydrolite History, which I think you can download from the Ocean Optics webbook pages if you're interested in the full history of hydrolite. Okay, so back to the radiative transfer. Now you know what hydrolite is. It's a software for solving the radiative transfer equation. How does it do that? Well, the first problem we have is this problem that I've already mentioned, which we talk about the radiance distribution in all directions. But we can't have on a computer the radiance distribution in all directions because that's an infinite number of directions. Yeah, we have to somehow have a concept of angular resolution. And this is the way that hydrolite does it. It breaks down that sphere of all directions into these, what we call quads, which are small rectangular segments of solid angle, which most of them are 10 degrees by 15 degrees, but there's an end cap at the top and at the bottom. And also the ones that are horizontally are kind of sliced in half like this. The reason for that is so that we can separate out the upper hemisphere of upwelling radiances from downwelling radiances. That's why you have this kind of slice across the middle here. And the quantity that we work with in the model is quad average radiances. So it's the average radiance in one of these quads, and that is the limit of the angular resolution of it. Okay, so I just mentioned we can talk about separate hemispheres. And, you know, so for example, the radiance propagating in a theta of 60 degrees would be represented by a number in this quad, and at 87.5 degrees, it would be represented by a number in this quad. But the radiances between all the angles there are just represented by a single number, which is the average radiance in that quad. So basically, we turn the whole sphere of all directions into 434 numbers. That's what it is, just a table of numbers of the quad average radiance in all those directions. Now, here's a limitation then, because features in the radiance distribution can be smaller than a quad. And the main example is the sun. So the sun, solid angle of the sun, is much smaller than one quad. But it doesn't mean that it's wrong. It just means we lose a bit of angular resolution. So what happens is the total, when we represent this as quad averaged, we have the quad average radiance in the quad. It's kind of more like this. It's the same number. It really is the radiance that you would get averaged over this solid angle, but we lose the ability to represent the sun as a small, very small solid angle. Most of the time, it makes almost no difference to the things that we're interested in, but it could make a difference in certain questions. If you want to look directly at the sun, then it makes a difference, because if you point a virtual sensor in hydrolite directly at the sun, you wouldn't get the right radiance, because you would get the quad average radiance spread out over a larger solid angle. But generally speaking, for most qualities like reflectance and so on, it doesn't make very much difference. And Kurt's written, there's a technical note about this angular resolution question about, you know, is it good enough and what difference does it make? And that's part of the documentation of hydrolite. In fact, you have that, if you've installed the hydrolite, you have that document on your computers already. So other models, I'll just mention, do this kind of differently. They don't have this kind of quad average radiance. For example, the discrete ordinates method, I think it is, uses what they call Lagrange polynomials, which is a way of representing, you kind of get a smooth function for radiance, azimuthally like this. And it's made up by adding a bunch of polynomials, which are orthogonal, essentially, which basically means you can fill up a radiance distribution of a certain angular resolution using them. But the trouble with that is, for me, is you don't kind of know what it is anymore. It's still got an angular resolution, a finite angular resolution. It's not magically adding information, but you've not, with the quad average formalism, you know that you're talking about the average radiance within a quad, and it's very clear what it is. And if you want to do comparisons against a Monte Carlo code, you can do that very precisely and very rigorously because you know the quantity that you're dealing with. If you use these kind of functions to represent the angular radiance, then it's kind of not quite clear what actually each ordinate kind of represents, to me anyway. So that's something I prefer this way of doing it. Okay, so just to go back to the radiative transfer equation, what we've done is we've taken this L, Z, theta, phi, lambda, and in one wavelength, we represent it by a table of 434 numbers. So for each wavelength we want to do, we have this table of 434 numbers. Let's just stick to one wavelength for now. So what we do is when we use this radiative transfer equation, we take this table of numbers and we just move it down through the water column. And we just modify it according to these equations. So we go through all the numbers, and the first thing that happens is the number is attenuated. So say we take a 1 centimeter step down in the water, and we take a number for that direction, and we just apply A and B at that point in the water column, reduce the number slightly, and that's taking care of the attenuation. And then we go over all the numbers like this, and we apply the phase function depending on the angles, and we just add that on. So it's just a simple thing of taking a table of numbers down through the water column and modifying it, and that gives us our radiance distribution through the water column. So it's kind of easy, yeah? Seems easy. But there's one thing I haven't mentioned or I've skipped over, is that it only works when you know the full radiance distribution. To be able to do this, at the top of the water column, you need to know the radiance in every direction, and then you can bring it down through the water column using the radiative transfer equation. But typically, we don't know the upwelling radiances. That's what we want to know. We only know the radiances derived from the sky. So we can populate the bottom part of this table of numbers, but we don't know what's in the top part. So it's a problem because then we can't do this. And what would happen is we could just put in some random numbers or zero. Let's say, okay, let's put zeros in there and propagate it down. But what would happen is that radiance distribution would change. And then when you got to the bottom boundary, let's say it's a shallow water and you have a bottom reflectance, that would not match the upward radiances and the downward radiances are now should be constrained by the bottom reflectance. They have to match up with the bottom reflectance. If you just start with some other numbers, it's not going to work. And this is what makes the problem difficult because it's a 2-point boundary problem. You've got the radiance boundary at the top, the input radiances, downward radiances, and at the bottom, you've got the reflectance of the bottom, or I'll explain how we handle infinite depth in a minute. But essentially, you've got a bottom boundary condition, and they have to both be adhered to. So you can't just launch in with the radiative transfer equation coming down through the water column because you're not going to hit the conditions of the bottom boundary. That's why solving the radiative transfer equation is difficult. The way I explained it, it seems like it's easy, but in practice, this is the problem. And this is why, for quite a long time, people's kind of struggled to come up with methods of solving this problem. So I'll give you an essence of the. I mean, there's no equations here, and you'll thank me for it. If I did show you equations, you wouldn't be happy. So probably, but I'll give you the essence of how it works. Is that instead of just launching in and propagating the radiance down through the water column, what we do is we talk about functions of radiance. Effectively, the reflectance is, we start at the bottom with the reflectance, which is a function of radiance in and radiance out, like a BRDF, yeah? And we propagate that upwards. And it's actually more than just the reflectance because it's the full sphere. It's a function of, but at the bottom, that we can say, if it's a actually got a flat bottom, we know there's no radiances coming the other way. So it's only just a reflectance. All we need is the downward and the upward. So we populate a big matrix which describes the radiance coming down and the radiance coming up as a function of the reflectance, and we bring that up through the water column. So in essence, instead of taking radiance down, we start by bringing reflectance up, just one little layer at a time. It's like adding a layer of water on top of it over and over and over again. And then we have the reflectance at the top of the water column. Then we can put in the sky radiance and get the upward radiances. Now we have the radiance field, and we can go back down again to populate the radiances through the water column. That's basically how it works. And that's what's referred to as the invariant embedded method. It's slightly more complicated than that, but that's the essence of it. But the issue is, what we're working with is a very large matrix of numbers now. I talked about that you can represent the radiance as this table of 434 numbers, but now we're manipulating matrices of 434 by 434 numbers, so really big matrix, and it starts to get computationally inefficient. So there's one other trick that makes it tractable, and that is that we exploit symmetries in the problem. And the main one is the azimuthal invariance of the scattering in the water column. So basically, if you have light coming in here, scattering out here, it's the same as if you just turn around, you twist around like this. So what we do is we apply a transform to these matrices that mean parts of the matrix turn into zeros. And so you've got a lot of zeros in those matrices. You can reorganize them, and the problem becomes much more tractable. But it relies on this situation of having the azimuthal invariance, the fact that light scattering in one angle coming out here, you can just turn around like this, and you've got the same angle, and that would be the same. So if you have orientated particles or something like that, where that isn't true, if the particles are all lined up like this, and you go like this, and it's this, and that's different to being over here and going like this and this, then you can't use this method. So there are limitations to what you can do with this kind of solution methods. I mean, you can do it, but you have to then use the full matrices, and it becomes computationally very inefficient. Okay, so any questions on that? So the point of that is just to give you a flavor of what's involved. Yeah, like it's everybody got a flavor of what's involved. I hope so. Okay, one thing I haven't mentioned is the air-water interface. How do we deal with that? Well, I think Darius showed the Fresnel equations. If the air-water interface is completely flat, then reflection and transmission are governed by the Fresnel equations. And this is a fairly well-known thing. It depends on the refractive index of the water. So actually, if you have high salinity waters with different refractive index, it's very slightly different. And you'll see in hydrolite, you can actually put in salinity or change the refractive index directly for that. So that's if it's totally flat. You have this kind of simple relationship, and you can just code that directly into the model. But of course, the water surface is generally not completely flat. Oh, there they are. So that's what they look like. And in fact, this is the one from the underside. So here you see the total internal reflectance. Here for a certain angle, which was, I can't remember, it's 50 something, maybe 48, something like that. So this is where you have total internal reflectance. So this is all captured by the Fresnel equations. Typically, the water is not completely flat. It's a very extreme scenario if you model totally flat water. So what we tend to use, it's very common, is the results of this Cox and Monk wind speed wave slope law. So this is a really important result. It's a really good piece of work that was done in the 1950s by Cox and Monk. And basically what they did was they had a boat, and they took photographs of the sea surface under different wind speeds from the top of the mast of this boat, and the images look like this. And from this, they were able to derive from the sun glitter patterns of the surface of the water, they were able to derive this kind of statistical model of the slopes of the surfaces. So what they came up with was this thing that the mean square slope, which is basically the variance of the slope along the wind in the along wind direction, is just a simple relationship, linear relationship with the wind speed, which is U10. That's the wind speed 10 meters above the water surface. That's just the one that we generally use as a reference. Let's call it U10. It's a simple linear relationship, but it has the limitations. This is for open ocean conditions with what they call a fully developed sea surface. So the idea is that the wind has been blowing at that speed for a long time over the sea surface, and you get, you have larger waves develop, but you also have these little capillary waves. So it's all spectrums of waves, from little millimeter capillary waves to bigger gravity waves that have developed over a long period of time, and possibly from a long way away. So this is why it's a kind of open ocean, ideally open ocean model, because if you had other things, or if you're in shallow waters, the sea surface slopes would be different. So this is strictly speaking valid only for these kind of conditions, but it's an incredibly robust result considering the way they did it and when they did it, because other people have looked at this since using radar techniques and all sorts of other techniques, and actually this relationship to first order is very, very good, and there's never really been any reason to stop using these particular coefficients that were derived back in the 1950s. So from this, we can develop a model of a sea surface that has a kind of a slope statistics, yeah. And it will kind of look like this. And what we do is we map the Fresnel equation onto this roughened sea surface, essentially. So locally, the sea surface is flat. So the light comes in and you apply the Fresnel equations where the sea surface is flat, but obviously twisted at a slight angle. And then you just average that over the whole surface based on this statistical model of the sea surfaces. And you get a function for the transmission and reflectance of the radiance on the sea surface, which is obviously more diffuse than the pure Fresnel equations. Like when you had your laser, if the water's totally flat, a beam of light will just transmit directly through, like a very narrow beam of light. But as soon as you have this roughness, it's going to spread the light out a little bit. That's one way of doing it. But the thing is, it's only a slope statistics model. So you see this, it has the right kind of slopes, but it doesn't have any vertical structure, which is what you actually get on a real sea surface. So there are some more advanced models that can build an actual physical sea surface that has the elevation statistics as well as the slope statistics. And these are both in hydrolite. So you'll see there's a choice for what kind of sea surface you want to use. And the default is the Cox and Monk, but it also has some sea surfaces that are based on these kind of elevation models, which have very similar slope statistics. The slope statistics are the same, but they also capture this vertical variation, but they're time averaged. So in other words, what happens is, and this is something that's pre-calculated because it takes a long time to do it, you generate a lot of sea surfaces for a given wind speed and a given refractive index. You do ray tracing to generate these functions, and then these functions are already pre-built and in hydrolite. So you just pick the wind speed and you pick a refractive index and it's going to apply that. So although these models have a physical sea surface structure, that actual structure is just averaged over time. So it's still a plane parallel model. It's time averaged. Okay, so this is just a kind of visual. Oh, any questions on that, by the way, before I? Oh, yeah, okay, cool. Well, it's an approximation. Yeah, I mean, it's a problem where there you have to do a detailed analysis to find if it was actually a problem. I mean, the best way, in some ways, to understand this sea surface stuff, I think, is that you use the wind speed as a proxy for sea surface roughness, rather than literally interpreting it as a certain wind speed. I mean, that's a good starting point. So if you measure the wind speed in a coastal area of 5 meters per second, yeah, okay, then you can put 5 meters per second into hydrolite. But what I tend to think more is like, well, is the sea surface rough or not? And I'll just put in a number. If I think it's a relatively flat sea surface, I'll put in a low wind speed. If I think it's a higher, if I think it's rough, I'll put in a higher wind speed. So it's more like a proxy for surface roughness. It is sort of the way I tend to interpret it. It's okay, because it is. I mean, but to actually understand what happens in a coastal area or in a non-fully developed sea is quite well. The non-fully developed seas you can do, but in a coastal area, of course, because the waves are coming in, and then you've got the shallow. It's coming shallower like this. It pushes the water up a little bit. It changes the waves. The waves diffract or refract around objects, and it's very complicated. So you can't really do any better, to be honest. Yeah. Yeah, you could use it. Now, I don't know exactly know how you go about that, but what I imagine is the sea surface roughness from the satellite is probably derived from the Cox and Munk equations. So you probably have or there will be some sort of, maybe there's some synergy there. I don't know exactly how it works because it's all very circular because, of course, the Cox and Munk equations were derived from sunglin, which is actually an optical property. So you're going from an optical property to a physical one back to an optical one again. So, mm, yeah. But do they capture the smallest waves? So that's you need. I mean, I don't know how this stuff works, but the thing about the sea surface modeling is you have to capture all of the slope statistics, and in fact, the most important ones are the capillary waves. Yeah, yeah, okay, yeah. Well, you maybe could then, yeah, you maybe could, yeah, but it's not something I know how you would do that. But yeah, okay, cool. Anything else on sea surfaces? Okay, right. Okay. So this is just a visualization to give an idea. So again, trying to reinforce it. You see that I kind of tend to try and reinforce things over and over again, just so you kind of get the impression of how these things work. I'm just, when you run Hydrolite, you've got a typical solution. Is the idea that you're bringing down this radiance distribution through the water column. What does that actually look like if you visualize it? And this is just a simple visualization to give that idea. So this is the downwelling irradiance, and these are kind of fisheye lens. Imagine like a kind of a fisheye view looking up at the hemisphere above, turned into a sort of pseudo color thing. And you see here's the sun. So you're already, I'll talk about the sky radiance in a minute, but because you're already at the bottom of the atmosphere, you've got a little bit of, it's not, the sun is not just in one quad like I kind of illustrated. You see a bit of a brightness around the quad where the sun is. So this is the sun. And then as soon as you go under the water column, then you see this is Snell's window. You can just see it here. So the sky becomes compressed into a smaller solid angle like this because of the refraction. And then what you see outside of that is the total internal reflection from other directions. So this is just under the water surface. And then as you go down through the water column, it becomes more and more diffuse. And here's the irradiance. And of course, the irradiance is getting less, and you see the red wavelengths drop out because the water absorbs most of the red. Pure water itself, that's down to. So that's kind of looking down, looking up as you go down. And this is a shallow water example, so it's got a sandy bottom. Well, most of my examples are shallow water because that's what I work in. So if we look at the upwelling irradiance, this is where you're close to the bottom. So this is looking down. At the bottom, you see that it's a Lambertian bottom in this case. So you see the sand, smooth kind of no features in terms of the radiance. But as you come up, looking down, you start to see a different radiance distribution because you're looking sideways through a longer path through the water as you come up. So you see darker edge. And then when you come above the water surface here, this bright patch is the reflection from the top of the water surface of the sun. So this is just below the water surface when you look down. And you can see some of this stuff to do with the BRDF that David was talking about. When you're just under the surface, if you look straight down, you see a different radiance than if you look over there. And that will also be transmitted. You can't see it so well here, but that's also transmitted through the water column to some extent. So this is where you have these kind of BRDF effects. And okay, so that's just a visualization to help bring home, like, kind of imagine what the model's doing. Okay, so David talked about this, and I shall repeat it in a sense to understand what happens when you don't have a bottom. So I just showed an example with a shallow bottom. So if you have the bottom reflectance, you can put in that as a bottom boundary condition. But what if you want to model waters that are effectively infinitely deep, or the bottom is so far away you don't really want to think about it, you don't think it's relevant, it probably isn't. And in that case, you can use this concept of the asymptotic radiance distribution. And what happens as you go down through the water column, and as David said, it's a theoretical result, but because we're working with radiative transfer theory, we can use it. That's a theoretical result. That's what we want. We're going to use that. And it says that basically, as you go down, the radiance distribution tends to a certain form. And that form depends on the IOPs. So we have to assume homogeneous IOPs. So after a certain distance, we just say, okay, the IOPs are the same all the way down forever now. And as you go down through that, the radiance distribution tends gradually to move to a situation where the radiance is downwards only. So I've got this example here, and I realize it's a terrible example actually, because it's the same from the, I just cut and pasted from the previous slide, and it kind of shows something. So as you go down, the relative radiance distribution tends to the same shape. The actual amount of light, of course, gets less and less and less, but the shape of it tends to become homogeneous. But this, although you see these diagrams here look kind of similar, what actually happens is that this bright spot moves to the center. So you lose all memory of where the sun was, because essentially after infinite orders of scattering, you know, the light no longer remembers where it came from, essentially. And actually the infinite, the asymptotic radiance distribution is an IOP, because it's only dependent on the inherent optical properties. It's no longer dependent on the sky radiance distribution. So there's a way to calculate that, and you can calculate the reflectance of basically an infinite slab of water with homogeneous IOPs, and you use that as your bottom boundary condition. So that's how you handle the infinite depth condition. So you'll see in hydrolite, you can either put in a finite depth with a certain reflectance, or you can just click a button that says infinite depth, and it will just take the IOPs that you specify in the model at the bottom and just say they're the same all the way down. And this just shows what, this is to point this out, all your K functions tend to the same value as you go deep. So David was talking about this, you know, your different K values are different in the as you come down through the top part of the water column, but because the directional nature of the radiance distribution tends to become constant, then all different, the Ks you might have, like the K for radiances or K for irradiances, they all tend to the same value because the directional nature of the light doesn't change. Okay, right. So as a comparison of hydrolite, for example, versus a Monte Carlo model, you know, we don't have this problem anymore of computational inefficiency. And in fact, the runtime is pretty much linearly proportional to the optical depth, which is the attenuation times the physical depth. So it will run slower if you put in heavily scattering orders, this kind of thing. But you don't have the same kind of problem with Monte Carlo, where it's really an exponential function of the optical depth. So, you know, you put more scattering in, then the problem just blows up to be really computationally inefficient. And you can put in profiles, arbitrary profiles of chlorophyll through the water column or other IOPs. So other models sometimes require you to work with discrete layers. So if you had a, you know, a data set from an ACS that showed a kind of wavy line like this for absorption, you know, you might have to, in another model, break that down into discrete homogeneous layers, a certain number of them. And then those models tend to have a runtime dependent on the number of layers that you use. Hydrolite isn't like that. It can just handle straight away the smooth function because it just does a numerical integration through it. And the solution includes all orders of multiple scattering. It includes infinite orders of multiple scattering just by the nature of how it works. So with a Monte Carlo model, if you have very clear waters with a very high single scattering albedo, you know, it can take a long time. You know, you're tracing a ray through the water column. It goes on forever, you know, before it comes out. It's got high scattering, not so much absorption, and it becomes very computationally inefficient. With hydrolite, you actually embodies infinite orders of scattering. So you don't have to worry about any kind of limitations there. Some other models will also have a kind of truncation of the orders of scattering. There's a modeling technique called the successive orders of scattering, where you do an iteration over the scattering orders. And so it becomes more computationally efficient, again, inefficient if you have a lot of scattering, but hydrolite's not like that. This particular solution method has no problems. So what time is it? I have 12. When's this lecture supposed to end? Is it, when did I start? Oh God, I've gone quite slowly. So it doesn't matter. Yeah, I started at 10 past though, so I guess I can go for at least, I won't be like wrong if I go at least to 22. So yeah. Okay, that's all right. So okay. Okay, so this is just a summary. I mean, this is really for reference about the features and limitations of hydrolite. I kind of mentioned all these things already, really, in one way and another, but I'll just point out a couple of key things. The wavelength restriction. So hydrolite, by default, when you use it as it comes, you can do modeling from 300 to 1,000 nanometers. That's no problem. It has all the data sets in there encompass that wavelength range. It's not an inherent limitation of the model, though. If you wanted to model down to 200 nanometers, the problem is simply that you have to provide the data yourself. And that would be a bare minimum, the absorption and scattering of pure water down to 200 nanometers, because the data in hydrolite only goes down to 300 nanometers. And anything else you wanted, you would have to provide it yourself. But if you provide that data, it will run no problem. It's not an inherent limitation of the model. What I will say is you have to be a little bit careful in the interpretation between below 400. So 300 to 400 nanometers, there's really not a lot of information that's known. I mean, I think Darius already talked about, Zongping already talked about, uncertainties in the absorption of pure water down to 300. There are uncertainties there. We don't really know very well, but there are numbers in hydrolite that have been put in mostly by Kurt relatively recently when we redid it, probably about 2017, using the best information that was available. But you have to be a little cautious about anything below 400 nanometers. Polarization is not included. I mentioned that already. It's a scalar model. And as David said, it's the same figures I've got here. That means that even if you're not interested in polarization, it makes a difference to the scalar radiance. So what happens is you need 2 orders of scattering for it to make a difference. So if you have a scattering event, just one scattering event, it doesn't make any difference to the radiance, whether you consider it polarized or not, the intensity of the radiance. But once you have 2, the first event will polarize the light potentially, and then the second one will selectively distribute that light depending on the polarization state from the first scattering order. So it means it's a second order effect. So it doesn't have that much effect, but at certain radiances, certain directions, you might see up to a 10% difference if you was to compare to a polarized version. But for things like irradiances, there's almost no difference. And in fact, I even think that this 10% figure, which I guess came from a study some years ago, I think that's a little bit high. I think almost never you see a difference that big. And then the other thing I'll mention at the bottom here, when you use hydrolite, you realize it has this GUI and you go through and you make these choices and you'll be like, oh, how could I use this to build a lookup table of 1,000 reflectances or something? I can't go through clicking it all. You can run hydrolite from scripts as well. So I've just put that bullet point in there because I realized I didn't have anything to say that. So you can drive it from a script if you need to build lookup tables and this kind of thing. I think I mentioned everything else already here, about the fluorescence and the other features there. Okay, so this is the key question. Any questions? Key question. Any other questions before we get onto this validation stuff? No, you can put in any depth if you want. If you can put in any depth. But what I'll say is, I was going to make this point later, but I'll make it now because you made the question. If you go really, really deep, then you can hit numerical problems as you could with any model. So if you wanted to say, oh, I wonder what KD is 10,000 meters into the ocean, yeah, where the model probably struggles because by the time you get there, the numbers are so small, the computer can't represent them anymore. And you start to get either rounding errors or at a certain moment, you might get a divide by 0. So it's only in very extreme conditions can you sort of break it in that sense, yeah. So there's no actual depth limitation. But if you started to put in tens of thousands of meters, you probably find the results. Usually it kind of blows up. You start getting not a number and stuff like this. Oh, that's resolution. No, not at all. So that's the point. Yeah, you can put in very thin layers and it will be able to handle that because of the way that it works. Yeah. Okay. Sorry, that was your question. Cool. Okay. Anything else? So I'll get on to validation. Okay. Oh. It's the same. It's tabulated in the. I'll go back, but it's in that same table. So basically, the angular resolution for scattering is treated in that table of 434 numbers. So it's the 10 by 15 degrees tabulation of quad average radiance. So the scattering functions are represented by a matrix of 434 numbers by 434, which is that angular resolution translated as an input and an output, yeah. So that's the angle, but that's the angular resolution for the scattering. So yeah, approximately 10 degrees. That's one way to look at it. Yeah, yeah. Yeah, exactly. So what Hydrolite does is when you put in a phase function, you can put your own phase functions in, and it has some already set up to use. It will uh, uh, populate that directional function at a 10-degree resolution everywhere, apart from in the forward direction. And then in the forward direction, it puts the remaining scattered light. So the forward direction is heavily peaked, but it's kind of accurate. So you don't lose any accuracy overall. But there is a slight issue there, which you're right, which is to do with if you're interested in what happens in very fine detail in the forward scattering direction, it tends to spread out a little bit more than it should do. Yeah. So if you, yeah, yeah, it does exactly that. Yeah. Yeah, it does. So this is an important point, but again, you only see it in the results if you look towards the sun. Really, is the only place where you really see this. So if you're looking directly towards the sun, what tends to happen is because you've got the sun averaged over a quarter of a finite solid angle, approximately 10 by 15 degrees, light goes into those adjacent quads a bit faster than it really ought to. So if you imagine the sun should be in the center of that quad and the scattering is forward, it shouldn't really be getting out of the quad so soon. But because you've averaged it over a slightly larger solid angle, it starts spreading out a little bit too much. Yeah. So if you look directly at the sun, if you look results directly at the sun, you won't see such a sharp forward peak in the radiance is actually what you would get. And you can show this with Monte Carlo. In fact, when you do a Monte Carlo comparison with Hydrolite, that's the main thing that you see is that the spread of a forward peak in the radiance, like looking directly at the sun, spreads out a little fast. But everywhere else, it doesn't really make any difference. So when you look at radiances from other directions, like usually you're mostly interested in the radiance coming up. And when you look at that, it makes almost no difference at all. It's just a slight increase in the scattering spread. Yeah, exactly. Okay, so validation. So important discussion, but what does it even mean, really? Validation. I don't know exactly what it means. You know, people say, "Oh, have you validated your model or whatever?" They don't say it to me because Kurt wrote this, so the software dies. People don't ask this very much about Hydrolite anymore. But you know, in general, when people say, "Have you validated your model?" What does it really mean? Well, I always say, well, okay, it probably means something like the comparison of model outputs to empirical data are of acceptable accuracy, whatever acceptable accuracy means. But an important exercise that we go through in our field often, you don't necessarily see it in other fields, I don't think so much, is this idea of optical closure. So with optical closure, an example would be that you go and measure your inherent optical properties, and at the same time you measure radiometric quantities, and then maybe you derive radiometric properties from that, AOPs. And then, so you've got empirical measurements of the light field, you've got IOPs, you have a model of the sky radiance, you put that in, and then you hopefully get the same radiances or the same irradiances or other radiometric quantities out from the model that you actually measured. And you want them to match. So you're going to the same thing by two means, measuring it and modeling it. And if they look good, if they agree with each other, then it gives you some confidence in your measurements and some confidence in your modeling. But typically, they don't really match very well. It's kind of rare that you would go and make some measurements, measure your IOPs, put them straight into a model, hit run, and then the first time it comes out, they match. Generally, they don't match. And you have to think, oh, well, what's gone wrong then? So what could go wrong in that process? Okay, so we've talked about the physical concepts. You've got things like the plane parallel assumption, the scalar approximation, the fact that we're neglecting polarization. These are the sort of physical concepts that are the assumptions that you've made in the model. Something else that could go wrong or be a problem, a source of error, is the solution method. You know, I talked about Monte Carlo models have a statistical error, or maybe the techniques that you use, like the directional discretization of the light field, the fact that you've got this angular resolution, maybe that's a problem. There's the implementation of the model. this is an important one. Maybe there's a bug in the model. Maybe something in the code is actually not right. I mean, it's basic, but it happens frequently, as anybody who's ever done any coding knows. And then finally, you've got the measurement of the empirical data. There could be uncertainties in your measurements of irradiances or whatever you're comparing against, or uncertainties in the IOPs that you've measured that you put into the model. So empirical measurement uncertainties. So how do we orientate hydrolite or using hydrolite against these aspects? So the physical concepts that are embodied in the model are well accepted. That's why nobody sort of asks, well, is hydrolite validated or whatever, because these physical concepts, the radiative transfer equation, these are well accepted within the scope of the model definition. So in other words, we accept it's a plane parallel model. We accept it's a scalar approximation. We know all of that. But given all of that, we think the actual physical concepts are correctly implemented. There's not really any question about that. The solution method, well, the solution method is what we would call an exact solution method, which doesn't mean it's exactly right, but it means given the inputs, it gives you the right outputs. But again, in the context of what the model is, it's a model for quad average radiances, and we've already discussed this a bit. So you have to bear in mind that it's exact within that context, within that concept, you know. And I just mentioned again, there can be numerical issues if you really push it hard. If you measure, if you want to have light, propagate light down to 10,000 meters, or sometimes people try to use hydrolite to do calculations for ice, and they're putting in scattering coefficients of 1,000 or 10,000 or something like this. That's really pushing the numerical capabilities of the computer, basically, and the way the model's structured. But I've only ever seen any issues with that in really extreme circumstances. I think, generally speaking, numerically, it's quite stable. Implementation, any bugs? No serious bugs found in quite a while, but I do continue to find little things sometimes. They don't really make too much difference. Again, they usually come to light when people do these sort of extreme things and sort of say, oh, it's not what I expected. And then you look in and you might find a little bit of something somewhere, but there hasn't been anything like that for a long time. And that's the benefit of a long-term code base that's been used by many people. I mean, the fact is all the users out there are doing a good job of like checking that it works, because if it doesn't work or if there's something, they get in touch with me and then we can get to the bottom of it. And there's not been anything for quite a long time. But what I always say to people is bugs are an ever-present danger. And I really do encourage people to get in touch with me if they see something weird in hydrolite. You know, don't just think, oh, it's hydrolite, it can't be wrong, it must be me. Please get in touch, because I always think you never know, and you want to stay on top of that. So it's an ever-present danger, but I don't think there's any serious bugs in the code anymore. So the key uncertainty then is in the measurement of the empirical data, really. This is the main area for doubt. You've got to measure your IOPs accurately. You're making some assumptions about things like phase functions and so on, because most people aren't actually measuring them. There are built-in options in hydrolite for these things, yeah, like the phase functions, and there's, as you'll see later, these biogeo-optical models where you can just put in how much chlorophyll it is, this kind of stuff. You know, they're just meant to be examples, really. They're meant to be there to show you how to run hydrolite, and maybe for a quick run to kind of decide how to, to do a quick sensitivity analysis or something like that. If you're really keen or you really want to make a good matchup to your own empirical data in your own situation, you really need to use your own data and use the right data there. So, don't just necessarily accept the built-in options, assuming they're definitely right for your situation, because they might not be. And some of the data in hydrolite is really not well known. It's scarce data. Like, for example, the CDOM fluorescence that's in there is just from one, I think it's actually somebody's PhD thesis, because the CDOM fluorescence is not very often measured in the way that it needs to be input into a radiative transfer model. People measure it, but they don't do it with the quantum efficiencies, which is the quantity you need to actually put it into a physical radiative transfer model. So it's got CDOM fluorescence in there. You can check the box CDOM fluorescence. Some people debate whether it's necessary. I mean, there's some papers that show that it was helped with the optical closure. There's other papers said, well, it didn't make any difference. So there's the jury's out on some of these things, and there's not a lot of data out there to know whether you know, the things that are in hydrolite are really right or not, for a few things like xenon fluorescence. So it's user beware is the basic advice. So I'll just give a couple of examples of papers that have done optical closure using hydrolite, and these are like kind of good examples, I would say, of like what you can expect if you do these kind of exercises. And the first paper is from Alberto Tinizzo, and this is a comparison of remote sensing reflectance. You know, and these are very careful studies where people have made real good effort to measure the IOPs carefully. And in fact, in this, they even had measured phase functions, but they compared them to the built-in Fournier-Farrand phase functions. And they were getting a measure errors, you know, within 20%, 23% between the spectral RRS that they'd measured and the modeled spectral RRS. So a kind of 20% error, that's basically not bad. And Giorgio, this is another paper here, looking at the average percent difference between the modeled and measured water leaving radiances. And actually, this is kind of a nice kind of validation, if you like, of the chlorophyll fluorescence, because what they found here is that with the chlorophyll fluorescence, if they model chlorophyll fluorescence, they've got a much better match with the water leaving radiances between the model and what they've measured. And there they're looking at averages. Well, it's the matchups were between 0 and 20% error, maybe averaging about 7% in the water leaving radiance. So that's really good. I mean, basically, I would say if you do an optical closure experiment and you're getting spectra matching within 20% for reflectance, say, that's quite good. You know, you can't expect an actually perfect match, you know. That's kind of just the practicalities of empirical data and the challenges in the optical closure of comparing two sets of empirical data, one propagated through a model and the other measured. The main caveat from the user's guide, I'll say it again, although I've kind of said it. This is the hydrolite model per se is a radiative transfer model, not a model of oceanic optical properties. It has those properties built in. It has example data sets for you to use, but you, the user, must supply the inherent optical properties and boundary conditions for the hydrolite core code. So hydrolite doesn't know anything about your particular situation. It has built-in data sets which you can use. Some of them may be quite good. Some of them may be, you know, like the pure water functions. Maybe you don't need to go looking for your own pure water scattering, attenuation, scattering and absorption functions. You can use the built-in ones for that. But your biological and geological components of your system, you might want to characterize those yourself, really. Well, you should too, really, if you want to get good optical closure. And the final thing that Kurt always used to say is garbage in, garbage out. So don't put garbage into the model. And then I think this is the final slide that I have. Maybe is it the final one? No, there's two. There's only two slides left. So I'm pretty much on time in the end. One thing, this is just a kind of practical thing to know. Actually, Dimitri asked about the vertical resolution in hydrolite. It doesn't really have a limit on the vertical resolution, but you don't want to put in really crazy, noisy, vertically noisy data like this, which is what you would kind of get as the raw data out of an ACS, you know, because you imagine you're taking your ACS through the water column, little particles are getting sucked in. And so you're getting very spiky data like this, where the spikes might be just individual particles, which kind of doesn't really make sense. You don't want to do a radiative transfer model of the scale, vertical scale of individual particles. Really, you want to smooth this data at least a bit. So you're inputting something like this as your vertical profile for this is A and C. Because although in theory there is not a limitation on the vertical resolution, if you try and put this into what is effectively a numerical integration technique, it will blow up because the numbers are just varying so rapidly, it won't really be able to handle that. So you want to do a bit of smoothing, vertical smoothing of your data before you put it in. And then the final thing I'll mention, because you'll see it, and in fact, one of the exercises this afternoon mentions it, asks you to run it, is ecolite. So ecolite is part of hydrolite. It's just a question that comes at the end of when you go through specifying the optical properties and everything. And all it is an azimuthally averaged version of the normal code. So basically, I've talked all the time about this table of 434 numbers, this radiance distribution. Well, what you can do is you can average it azimuthally. So instead of having discrete azimuth directions, you just have bands around like this. So it's much less numbers effectively. Instead of 434 numbers, you've got, what is it, 20 numbers, I think, to propagate through the model. And this is actually quite useful because in a lot of circumstances, you'll get the same answer out. If you're only interested in irradiances or the radiance directly up and down and any derived quantities of that, such as the remote sensing reflectance in a direct nadir view, then you'll get exactly numerically the same answer from Ecolite, but it runs a lot faster because it has less numbers to propagate. If you need to have, you know, radiance at an angle and a certain orientation, then you can't use Ecolite. But it's there as an option because it runs a lot faster. And sometimes maybe if you're building lookup tables or something, you would use Ecolite instead of Hydrolite because, as I say, it's much more efficient. All it is, as I say, it's specified just at the end of when you configure a run because it takes all the same inputs. So it's just a choice at the end, run Hydrolite or run Ecolite.